lesson that I'm covering. Okay, so for the particles in chemistry, right? How we discuss the particles, how many types of particles are there, right? Now, this is just a general idea of how the materials are distributed. Now, if I talk about the particles, I would say that the particles can be devised under the condition that how many types of particles are there, right? If there are only one type of particles, we usually call them as elements, and we may call each one as an atom, right? Now, the atoms can join together and form combinations of different types of atoms, or maybe of even one type, right? So they are called molecules. Okay, and if they somehow attain a positive or a negative charge, in other words, loss or gain of one electron, right, that would turn them into ions, right, the atoms. And if the same way molecules, which are bigger combination of atoms, they attain a charge, then they can also become ions, but we call them as molecular ions, right? So the examples are big molecules having their ions, right? I'm pointing these colored particles in there, these atoms, specific ones, which brought the charge with them, right? In other words, rest of the particle was actually neutral, but this particle brought in the extra charge, either in terms of the positive by not having the electrons, or by having excess electrons, right? So either way it can be charged, and these are uncharged ones, which we simply call as molecules, right? Okay. Some subject vocabulary, which is, I think, very important before we go into the topic of moles, right? Number one, atoms, right? What are atoms? They're the smallest chemically indivisible particle of matter that can exist independently, and that is the case of what, to be very sure, is the helium, the neon, the argon, right? All these noble gases, they exist as single atoms. They exist independently as well, right? Pure example of independent existence. Some may not exist independently, but we still call them as elements because they're only one type of atoms. Metals we usually consider as particles and move existing independently. Reason being, we can easily scrap off the metal, right? We can scratch it, we can remove some atoms from the top very easily, right? So they're easy to flow, they're easy to mold, they're easy to work with or scratch, because the atoms can easily flow over each other, right? So this is another example of like solid being existing as independent atom, right? We consider that those are independent atoms, each one can react independently. Okay, then ions, the charged species of atom due to gain or loss of electrons, right? Could be negative ions if they're gaining electrons, or could be positive ions, which could be due to the loss of electrons, right? These ones lost. So they are atoms which have now attained a charge. We call them as ions. Now, molecule, to define them, when two atoms combine together to stabilize and lower their energy, right? This could be an element or a compound, which I told you that if there are only one type of atoms in a molecule, for example, sulfur 8, right? So does not have any dissimilarity between the atoms. So we can call this as an element, but exist in the form of small particles called molecules, right? And then we have compounds, which also exist as small particles of molecule, but they are of different type, for example, water, right? So there's one different type of atom and the other one is a different type of atom. All right. Molecular ion. So an ion formed from a molecule, right? A big molecule retaining a charge, right? The simplest example is basically NH4 positive, right? The whole thing becomes positive, right? So we'll talk about this, how it attains that charge. But again, that's not part of our stoichiometry. We'll come to that like as an extra example. Okay, elements, substances which are only one type of atoms, compound, which are different types of atoms, right? So the examples are there. We have already covered this, right? Mixtures in which the substances exist independently. Now, why the vocabulary? Because the questions, the way they are stated in the paper, they require this vocabulary to be understood very clearly, right? So mixture, so it's a substance that is composed of two chemically different substances, right? It could be two different, right? If I say I have a can full of let's say there's a can in which I have hydrogen here, and I also have another gas which is hydrogen here, do you think they're dissimilar in any way? No, so this is not a mixture. So we will simply call it an element staying together, right? It's just an element. But if I say I have H2 gas and I have N2 gas, now this you will call as a mixture because they're two different chemically different substances staying together, right? So mixture are those which are two chemically different substances. So the emphasis is this word, right? Chemically different substances. So that's a mixture. Now it could be a solution. Now even in solution form, the independent chemicals retain their chemical properties. It's not like just because something got dissolved into something, it has lost its potential to react. An acid, even dissolved in water, is still an acid. It will still be very dangerous. It would be still reactive, right? The same way, okay, even though it is completely soluble. And then we have some substances that don't dissolve. For example, stones in water. You throw some stones in water, those are, let's say, granite, marble, anything, right? Calcium carbonate, they're not soluble in water, right? Over there still they will retain their individual properties, right? Unlike solutions, which is very pretty much evident. Okay, now some other words. Gas mixture. So whenever the question is referring to a gas mixture, that means two gases are coexisting together, right? Two different types of gases. Could be monatomic, could be diatomic. Monatomic means only consisting of individual atoms, and those are only and only and only noble gases, right? Nothing else. And other gases could be diatomic, would be hydrogen gas, oxygen gas, nitrogen, right? Chlorine, bromine. So these are gases which exist as two atoms staying together. And then we have polyatomic, that means could be more than that, like phosphorus, sulfur, if we turn them into to gases, like at very high temperatures. So there'd be gases but bigger atoms, right? Bigger chunk of atoms staying together, bigger molecules, right? Still, if we say that two or more of them are existing together, that's a gas mixture. Liquid mixture would be the same way when we have two different liquids that are staying together. And mostly when we say liquid mixture, then we're usually referring to insoluble parts, right? This is just a mixture that they're not fully soluble. If we say solution, then the word definitely rings that it is a combination, a mixture in which two substances are fully dissolved into one another, right? You cannot differentiate the properties very easily, right? It's very hard to identify that any one point in that solution would have any different properties than the other part, right? For example, sand and water. So sand would sit at the bottom, would be more sandy water at the bottom, and would be more clearer water on the top. So that is not very well distributed properties, okay? Now, precipitates. The word precipitate, when used in the question, it would refer to any solid particle which is formed in a solution which does not dissolve, right? So we will come across solubility rules this year. I would advise you to memorize those because it will greatly, greatly enhance your ability to crack the questions faster than usual, right? Okay, so precipitates are solid formations whenever two solutions react together, right? This is after a reaction. Remember, this only happens when a reaction has occurred. Usually does not exist on their own. After a reaction, it is formed. Okay, solid solution. When two metals are staying together as a solution, right? It's a solid solution. So example is steel for us, right? And then we have stainless steel, which is this one, and then we have brass, which is this one, right? The copper one. Oh dear, let me just put it aside. Okay, so this is what brass looks like, right? Copper and zinc combination. Dissolution, right? The word term dissolution will be used for the process of dissociating a substance into its ions, right? For example, acids dissociate in water, salts dissociate in water, not all of them, but some of them, right? Acid, we say that any acid that is not soluble in water is a weaker acid, right? The stronger acid we say are the ones that fully dissociate in water, right? That is from acid and bases, right? A little concept. And then chemical symbols, the alphabetical letters that represent the elements, right? Chemical formula, it is the alphanumeric way of describing a substance, right? So it's a formula of these chemical symbols that represent a compound, right? For example, HCl, for example, this S, what would be carboxylic acid, right? So it's a 1 2, right? Dicarboxylic. No, 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 it is two carbons. Two carbons would be hmm methane. What's the second carbon called? Saurabh. First one is methane. Ethane. So this is ethanoic acid, right? Okay. Uh, If you remember, we did this nomenclature at the very end, right? Okay, so I'll have to do this some reinforcement over there as well. Okay, only metals, monatomic gas, and written in individual symbols, right? So remember, monatomic gases and metals, they're usually written as single, like this, right? Single atom. You don't need to specify number. For example, for hydrogen, we write H2, right? Because two atoms are staying together as a molecule, so we don't have to put two of them, right? For metals and for monatomic gases, they usually are counted as one over here, right? At the bottom, only one whenever you're using reaction. So if we want to balance them, we'll actually have to add a coefficient over here rather than the number of atoms over here, right? We'll balance it from here. Okay. Okay, atomic number. Now these are the definitions we need to understand what mole is getting into, right? Atomic number, the number of protons or the position of element in the periodic table, right? So I'm not going to go into periodicity because you already know this very well, right? Uh, Again, mass number, sum of the protons and neutrons, right? How many protons are there, how many neutrons are there, and why we call it the mass number? Because the majority of the mass of the atom is inside its nucleus, right? The majority of the mass is inside its nucleus, right? That means the electrons are very, very, very less weighted than them, right? So I think one proton by weight would be like one electron, right? One electron would be probably the mass of 1 over 18 something something, right? 1800 roughly, you can say, protons, right? One proton. Compared to one proton, it is that little, right? And neutron is slightly heavier than the proton. But again, this data is actually provided in the data sheet, so I'm not going to go into this, right? Nonetheless, our focus is on moles here, right? So, relative atomic mass. Now, what is relative atomic mass? It is the mass of a single atom compared to the mass of carbon C12 atom, right? For example, for hydrogen, we use this mass in some of the periodic table, right? Some of the advanced periodic table you'll find which note this value, right? 1.008. Why is that so? Because this shows that the atom is a still, comparison with the carbon C12 atom, how heavy or how light it is. But the unit over here is not grams. So please mind, whenever we use these values to describe one atom, we always write AMU, or atomic mass unit, right? And for the chlorine, we actually have 35.5. If you remember, chlorine is 1735 in general when we write it, right? But why the 0.5 there? There is no half proton there, right? So basically, the sum of all the protons and the neutrons, they add up to give these fractioned numbers, right? They're not entirely one and one, right? So we just, if we compare it to the carbon C12 atom, right, then we say that it is slightly above the, you can say the fraction over here, right? It's not entirely 35. It is 35.5 for the single chlorine atom, right? Again, atomic mass unit, written as AMU as a unit itself, right? This is a quantity. Remember, relative atomic mass is considered in AMUs. Yes, we can convert AMUs into grams, but for that we need to enter the concept of moles, right? We'll come to that in a moment. So, what are isotopes? Now, isotopes are atoms of the same element that have the same number of protons, but they have different number of neutrons. In other words, the mass number is different and the atomic number remains the same. As you can see, for hydrogen over here, the atomic number is the same, but the mass numbers are different over here, right? So these are three different isotopes of hydrogen. This is called protium, this is called deuterium, and this is called tritium, right? So these are three names. No need to remember the names, but just to give an idea that the three different hydrogens, and all three of them are chemically same. Now keep in mind, all three of them will make water. Surprisingly, we use the water made from this second isotope, which is the deuterium. We call it heavy water, right? Why heavy? Because it uses a heavier isotope of hydrogen than the usual isotope of hydrogen that we are accustomed to deal with, right? Okay, then oxygen also has two isotopes, and by the way, we're breathing both of them, right? Both of them are running the same chemical reaction inside our body, right? This is basically about, I think, 70 to 80% in the air, right? And the remaining is this much quantity, right? So both of them add up to give you air, right? Oxygen inside the air, which we call as to overall 21% of O2. Now remember, this O2 has both of them, keep in mind, right? And their own specific concentrations, right? So both of them add up to give you this 21% O2. So breathing both of them. So again, they have no chemical distinction compared to their other elements, right? So it's the same element, nonetheless, irrespective of the mass. Okay, same is with the uranium, right? We've got several isotopes of uranium, right? Okay, now, relative atomic mass from percentage abundance. Now, we want to convert, how the percentage abundance defines the central mass that we use in the product table, right? Because in the product table, I cannot write like the atomic number is 8 and the mass is 16, 17, 18. Let's say I've got three isotopes, right? So would be confusing. So we generally write the averaged mass of that element over 8, let's say 16, then it is 16.02 or something. So that means this is the average of this relative atomic mass that we get. And how do we get that? We simply take the how many number of isotopes are there. Let's say for oxygen there are two isotopes, so I'm taking two of them, right? One here, right? Which I said that the mass of the isotope, right, whatever the mass is, like for oxygen is 16, the percentage is 70%, let's say, right? This is one element covered, plus the same way I have to repeat the same process, that the mass into its percentage, right, plus mass into its percentage of how many you can say the isotopes are there. For example, for uranium, I need to repeat this step by adding these together at least three times, right? Three of them would be there. So I need to know the masses, independent masses for three of them, and I need to know their percentages, how much percentage they're available in nature. And then I can calculate, dividing by 100, I can calculate the atomic mass unit, or the mass of a single averaged uranium atom. For example, this is 50% in nature, this is 30% in nature, and this is 20%, right? So I get their mass number and their percentage, right? And each one, and add them up three times, like, and then divide by 100. I get the AMU answer for this, right? Which is for uranium, I think is 232 point something, right? Because these two are in lesser percentage. This one is more abundant and hence very bad to use, right? In terms of its application in energy sector, right? These two are more viable for energy sector, but we have less of them. So we do an enrichment process, if you must have heard during this like the Iran event, right? We were talking about like enrichment labs were destroyed and whatnot. So what they do in the enrichment, they convert this isotope into its heavier counterparts, because there are less percentage to be found on Earth. So, and we once they're done with this, so its energy levels are higher in terms of energy applications, right? We do just an enrichment technique on this. So this AMU actually gives you the average mass of all three of them together, right? Are you with me so far? Okay. Now, molecular formula. Now, as I said, we'll be getting into moles, so this is just the beginning, right? Molecular formula is the formula that shows actual ratio, highlighting this actual ratio between the atoms of a compound and molecules. So it represents the actual ratio in which that compound would be formed, right? For example, if I write NH2, or let's say I say nitrogen gas is N3. Do you agree on this? No, right? Because they make three bonds to fill their outer shell, so it would be N2, right? So the N2 or N3, these are two different formula. If N3 did exist, it would have its own unique chemical properties. So a formula, a molecular formula, is the one that represents a unique character of that individual molecule, right? For example, for the ammonia, it's a base, right? Why? Because we have one nitrogen and three hydrogens joining together, so it has its own discrete chemical properties. Water has its own. We have benzene over here, and then we have glucose over here. So this all four of these formulas represent the actual ratio in which the atoms are reacting, right? For example, for ammonia, right, what is the ratio between them? It is 1:3. That for each one atom of nitrogen, I need to join or provide three atoms of hydrogen to make ammonia, right? Otherwise, if I provide less, then at least ammonia is not gonna get formed, right? That's not what gonna be the at the end of the reaction. Okay. Same way for glucose, it shows 6, 12, and 6 ratio between the atoms between carbon, hydrogen, and oxygen, right? So we'll learn to use these ratios once we start doing the calculations, right? We have a question called identifying the molecular formula of an element, right? Of a compound, sorry, right? So for that, we'll come back to this in more detail, how to write these. Okay, empirical formula. This represents the simplest ratio between the atoms. Now we can only simplify up to whole numbers, right? For example, 1:3. Can I simplify this more? Whole numbers? No, right? Can't be. But if I say between benzene, right, we had 6:6. That's the molecular formula. Can I simplify this? What would be the simplified version? 1:1, right? So I can write this as CH as an empirical formula, right? So why we have empirical formula? Because we'll understand this in A level, right? Once we go into spectrometry, that identifying uh, organic compounds using their fragments, right? So the empirical formula helps us there, right? Unfortunately, here we just need to tell you that this is an empirical formula, right? And the empirical formula represents the simplest ratio between, right? Simplified ratio. As you can see, these two compounds have been taken from top, right, like this. And if you look at them, then these simplified versions are just the simplified numbers, right? Eventually, it does not show you the actual compound formula, right? It does not again show you the actual compound formula. So remember that compared to the molecular formula, this is not actual. Okay, clear about this? Okay, now molecular mass. This is the sum of all the masses of the atoms in an empirical formula or a chemical formula, right? Sorry, I said empirical formula. It is chemical formula, right? In a chemical formula, whatever the number of atoms are there, we need to add their masses. For example, for water, we have two hydrogens, and like 2 multiplied by 1, which is the mass number of the hydrogen, and plus the next atom, which is oxygen. Since we have only one of it, so it's multiplied by 1, and we add them up, we get the atomic mass unit version out of it, right? Again, so far we're not talking about grams. How do we convert it into grams? That's the concept of moles, right? Now, what are moles? This is the quantity of a substance expressed as formula mass in grams of a mass having Avogadro number of particles, right? So we can say that any substance that has a very specific number of particles in it, right? Now, which is, I'm saying the Avogadro number, this number, right? This one. So any substance that has this many particles is going to be called as 1 mole, irrespective whether they're atoms, whether they're particles, whether they're molecules, right? Whether they're big chains of molecules, right? As long as we count discrete particles, right? And they have this much in number, right? 6.022 into 10 is power 23, right? This is the Avogadro's number. Then we call that substance being 1 mole, right? And what would now be atomic mass, right? The thing that we are concerned with, like grammage of a substance. Then we say that the mass number of an element expressed as gram per mole. In other words, how many grams would 1 mole of a substance weighing, right? For example, for hydrogen, it is again 1008 gram per mole. Now remember, AMU was the mass of only one particle, right? This is particle level, right? This is one particle, I'm saying, right? This is 6.022 into 10 to the power 23 particles. Are you clear now? Right? When we put this number with the particle, then the mass is now expressed in grams. You can only express grams if you're talking about this many particles together, because obviously the mass of one atom is insignificant compared to what we are doing. And especially you talk about factories, they are working in tons and tons, right? So if we started explaining number of particles there, how many atoms, because we can only describe atoms as particles, right, in chemistry. So if I say that I need 6 atoms of carbon to react with 6 atoms of hydrogen, unfortunately in nature hydrogen is not found as a single atom, it is found as a double atom, number one, right? Carbon is found as a big chunk of large number of carbon atoms staying together, right? Let's say graphite or coal, right? Huge number of carbon atom. No, I cannot find independent. So it would be hard for me to identify that how much of that chunk of carbon I need to take and how much of the hydrogen gas I need to take from the air to react together to make benzene, right? It would be very hard if I started counting numbers. So this scientist devised the idea that if we take 6.022 into 10 to the power 23 number of particles of any substance, we're going to call that big number of particles staying together as 1 mole, right? And that 1 mole can now be expressed in terms of grams, right? That 1 mole of a substance is the natural weight of that substance in grams, right? Are you clear about this so far? So, in other words, if I say 1 mole of water, right, to which we just calculated that it is 18 AMUs, right? One molecule of water, right? One molecule of water weighs 8 or has a mass of 18 AMU, right? If I take 1 mole of water molecules, right, 1 mole of them, that is 6.022 into 10 is power 23 molecules, right? As I said, particles could be any particle. You can even count electrons in the same way, right? So that should now weigh 18 grams, right? Because from here we can also depict that this is 18 grams per mole because it's for 1 mole, right? Per mole. So 18 grams it weighs for each mole of water, or this many molecules of water, right? 6.022 into 10 to the power 23. This is the birthplace of the concept of the moles, right? The most trickiest concept that the kids think, right? But if you grasp the idea that 1 mole only represents the number, we are trying to simplify the count of atoms. Because why do we need to count the atoms? Because we can only identify their structures, molecules, or their properties by how many atoms are staying together, right? Or the molecular formula. So to describe the mass of one formula, we use a quantity called moles, right? This is what I've written it in this statement, that quantity of a substance expressed as formula mass, right? That means the mass of one complete formula. It could be empirical, it could be anything. Usually we don't use empirical, we call it empirical formula mass, right? Not molecular mass. So getting to the term molecular mass usually is used wrongly even in your books, right? That it is in grams, that is not molecular mass, that is called molar mass, right? The term is wrongly used even in the books. I don't know why some writers are doing it, right? But you can say that yes, when the molar mass is expressed in grams, then it is also the molar mass, right? When the molecular mass is expressed in grams, it is also called molar mass, right? This was like term used in the old books. Now the new books, I don't know why they're mistaking these two terms to be the same, right? One is in AMUs, right, unless expressed in grams, and if we express it in grams, we are sure that it is at least containing this many number of particles in there, right? While the molecular mass could be of one molecule independently as well. Okay, clarified here or a bit confusing? It's fine. Okay, fine, fine, fine. As I said, we'll understand this far better with the questioning now, right? So then we talk about balanced equations, that the number of atoms at the start of the reaction and at the end of the reaction, they need to be balanced, right? How many atoms are there for hydrogen on the left hand side? 4. And how many for the oxygen? 2. And now on the other side, 4 and 1. Are you sure? 2 has 2 is multiplied with both of them. It's a joint formula, right? So 2 again. So this is called law of conservation of mass, right? Now you understand where we are concerned with number of particles, even though it's a very big number for us to deal with, what the headache it is, right? But why? Because we know that chemical reactions only occur in a balanced way, right? They cannot be an atom going missing or atom coming out of nowhere, right? It has to be accounted for. This is called law of conservation of mass, that the mass before the reaction and after the reaction must be equal. Let's say some kids tell me that you burn something, the paper was heavy, after burning the paper got light, so that law of conservation of mass does not hold. What do you think about it? You have a paper ball, let's say it's got 18 grams. I put it to fire. After catching fire, only the ash is left, but now the mass has reduced to 10 grams. Where did the 8 gram go? Yes, in the air. Very right. In the form of gas, right? So if we did the same thing inside a closed jar, right? In a closed jar, do you think the mass would change on the balance? No, it's a closed jar. The gas is not going to go anywhere. Uh, yes, it would. We weigh, oh my dear, once we go into as I said, the calculation, the industrial implications of this mole will be working with tons in gases, tons in mass of gas flowing per minute, right? That's the amount of gas we're going to be pumping through factories, right? We're going to talk about atom economy at the end of moles and whatnot, right? So we will be going into this, right? So let's begin with the formal concept of the moles now, right? So word equations, right? Just to give you a distinction again, like what word equations mean, right? They mean that you have to write the chemical formula in words, right? Instead of describing in symbols. If you miss even one out of them as a chemical symbol, let's say you just quickly, you were short on time and you just wrote O2, then you're going to get marks deducted for this. You have to write the whole thing as words, right? Only. So just an exam hint over here, right? How to tackle the question. Now remember, the law of conservation of mass holds that as many number of particles going in should be there even after the reaction. This is how we balance the equation, right? If the atoms are not balanced, we need to keep iterating our equation so that they become balanced. And this will devise an easier method for us to run our reaction and do calculations. Now I would know, right? Let's say I do know that the 2 mole of hydrogen gas weigh 2 grams, right? And 1 mole reacts with, right? It reacts with 1 mole over here. And how much do you get? 2 mole of water. Let's say this makes my life easier, right? I know that this is 32 grams and this is 18 grams, right? So I need to get two of them. Okay, 1 gram multiplied by two. So if you look at the grams now, does it add up? 2 plus 32. Yeah. Oh, sorry. 2 plus 2, or 2 into 2, sorry. 4, 4. 4 plus 32 is 36, right? 36 should be equal to 2 into 18, which is also 36. So, yes, the law of conservation of mass holds. Now you understand, by describing the moles, it was easier for us to count the grammage or the tons or the kilograms, right? Now, instead of counting the atoms that, oh, I need to pump maybe a trillion more atoms of hydrogen to run the reaction, right? It would be very hard. I can just simply tell you that add 20 more grams of hydrogen in there. Easier to work, right? Weighing is easier than counting atoms, right? Invisible particles, especially when they are very small and very hard to identify, right? So it's easier that we can just weigh the mass and then we can put it in there. Is there a way to measure a small fraction of a volume, the mass of a gas? How can you do that? If let's say I have a reaction chamber that is producing a gas, I want you to take a certain mass of a gas, collect out of it. How would you measure the mass of a gas? Easiest way. Think like a child. Huh? The gas itself, out of nowhere? Aren't you gonna catch it into something? Yes. Collect it in a balloon and weigh the balloon, right? Weigh the balloon before filling, weigh the balloon after filling. That should tell you the mass of the gas. And frankly, some gases are quite heavy, right? They actually feel very heavy, right? and most of them are also dangerous in that regard, right? Because those heavy gases are dangerous, right? We can't breathe them. They suffocate us, right? Very quickly. So, like what? Like many gases, for example, lots of uh, uh, propane gas, right? If I leave it, it's heavy, all right? If you're on the floor, then you won't be able to breathe. It will push the oxygen atoms away, right? Because it's heavy, so it will settle down and it will push the oxygen above, right? So you won't be able to get breathable oxygen at the bottom of the floor if it's in a room, right? Or butane in that regard. So any heavier gas. So just like liquids, right? Heavier liquids, they settle down. Lighter liquids, they move for. Yes, it would diffuse as well, but majority would settle down. Like carbon dioxide settles down, right? Cyanide and many other gases, they settle down, right? Heavy gases. Bromine gas is an example. Very heavy gas, cannot stay floated for much, right? It would rather settle on the floor. You'll find, like, if I take a bromine cylinder and just keep it open inside a room, and if it's at room temperature, you'll find there's a brown cloud on the floor, right? Not in the whole room. Some of it would be diffused, energetic particles only, but majority of it would be on the floor as a cloud, right? It would be a gas, but heavier gas to settle on the floor. And at that surface, you're not going to get any hydrogen or oxygen out of it, right? Because it's too heavy, it has displaced them. Okay, three equations that I want you to remember, right? Especially when we're talking about solids, when we're talking about liquids, and when we're talking about solutions, right? So, three different equations of moles that we're going to be working with. When we're talking about solid materials, then we can calculate the moles by knowing that whatever the given mass is there and what is the molar mass of that component, right? So we can get the moles of that component by this equation, right? Remember, I'm representing moles with the symbol N, right? It's a universal symbol used for moles. And M represents the given mass, and MR represents the molar mass, or also termed as molecular mass in your paper as well, right? So don't get wary about this if they use these two different terms. It's the same thing, right? F expressed in grams. Okay, so the unit would be gram over gram, so the gram cancels out and the mole comes up, so you get mole, right? Again, this is the balancing of the units, right? So in liquids, we can talk about the given volume, right, over molar volume, right? Especially sorry, this is not for liquids, my bad, this is for gases, by the way, right? My apologies. So this is for gases, right? So we have, let's say if it's a gas, we have its volume, given volume, and we know its molar volume, then we can calculate that how much. And remember the molar volume for your paper, right? Vm would have a value of 24 dm cube. That means if I have this many particles of any gas, I'm saying any gas, at RTP, then it should occupy this much volume. Okay, are you clear about this? Right? So if I have this many particles, irrespective, they're atoms like helium, they're molecules like hydrogen, they are bigger molecules like cyanide gas, as long as they are at room temperature and pressure, they would occupy this much space. They should, right? And this is a constant that we're going to use. So we have a constant value here, right? Compared to the other ones, which like depend upon the number of atoms that are there in the formula, right? And then if we're talking about solutions, then we can talk about moles in terms of concentration into volume. And this is actually for liquids, right? I miswrote that over there, right? This is for liquids, right? So the concentration into volume would give you the number of moles at how much concentration it is, right? It is concentrated, and how much volume of that liquid is there, right? So we usually express this as mole per dm cube, which is the unit for concentration over here, right? And dm cube, and they cancel off, so you're already left with moles. Okay, so very fascinating idea. So let's now start with molar calculations, right? Molar calculations. How do we make molar calculations? Okay, so I told you that the three formulas: n is equal to m over mr, right? The other formula is n is equal to v over vm, and the third one is n is equal to uh, cv, right? Concentration to volume, right? That's the only one which looks a bit different. These two look alike, right? They're same. And we can actually go interconversion, because if we're talking about we compare the moles of a singular substance, then we can equate this as well, right? We can equalize them as well. Okay, so let's start with a very, very simple formula, right? A simple question. Calculate the mass of uh, 20 uh, oh, let's do uh, what which should the mass, no, not mass, moles. Yeah, let's calculate moles first, that would make it easier. Let's calculate the moles of uh, 18 9 9 grams of water. Let's say you took some water, you weighed it, it was 9 grams, right? How many moles are there, or in other words, how many particles are there? Also tell number of molecules, that how many molecules are there in that 9 gram of water, right? Why we develop this concept of moles, right? So we do know that the number of moles is given mass over the molecular mass, right? We do know that this 9 gram is basically the given mass or the mass of that substance, and mr for water is basically 2 plus 16, making it 18 grams per mole. Remember, this is molar mass, right? So putting in these values, n is equal to 9 by 18 or 0.5 moles, right? So only zero point 0.5 moles of water are there if you have 9 grams of water by mass, right? By mass I'm talking. And it doesn't matter wherever you take it, because you do know the mass does not change, right? Universally, it's a universal quantity. It just counts how much of the substance is there and how much it weighs, right? So if we have only 9 grams of water, this many moles are there. Now, if I want to calculate the number of particles, right? So remember the number of particles, given particles, right? Particles in given mass, right? That should be equal to number of moles into the Avogadro number, right? So we know we have zero point 0.5 moles only, and 1 mole is supposed to have this many particles, right? By virtue of Avogadro's number. So half of it is going to be 3.011 into 10 to the power 23 molecules, right? That many water molecules would be there. Now you can even tell about how many particles are there, surprisingly, right? Just by knowing the mass and knowing this molar formula, right? Molar conversion. Just by doing a molar conversion, we easily accounted for the number of particles that are there. So I can now devise the reactions just by balancing the moles instead of balancing the number of atoms that are supposed to react, right? Because for example, for water, the ratio is 2 ratio 1, right? Two hydrogen atom must combine with one. So can I tell, like if I have, let's say, 3.011 into 10 to the power 23 molecules of H2, right? H2 only. How many of the oxygen do I need? Of H, sorry, H, not H2, only H, right? Or let's do oxygen to make it even easier, right? Oxygen. How many hydrogens do I need? Double as many. So 6.022 into 10 to the power 23, right? How many moles of hydrogen would be there in this much? Moles. 1 mole, right? Is exactly. And this would be now, since it's half the value, this is half a mole, right? So if you check it, what is the ratio of their atoms now, right? Will they react equally or not? So we say that 1 ratio 0.5. I told you we cannot have decimals, so we have to convert this or adapt this so that they're whole. Yeah, so it would be 2 to 1. So again, are you getting the same point over here? What is the actual ratio between hydrogen? So again, if I just tell you, instead of talking about the atoms or particles there, I can tell you that I need 1 mole of hydrogen to react with zero point 0.5 mole of this, right? And in terms of gram, you do know that the gram would be 2 grams for this, and this would be 32 minus this 16 grams, right? O2 and H2, right? So no, it is already halved. These are atoms, right? So for each 1 gram of this, right, this would be 1, I need zero point 0.5 grams of this. Now can we equate the grammage as well? It is 1 gram. Sorry, sorry, sorry. It is how many gram? 16 grams or 8. Sorry, my bad. Right? 18 gram, 8 grams of this, right? Because zero point 0.5 mole of oxygen we're talking about, not O2. I'm mistakenly taking O2 and H2 again and again, right? Okay. So for each 1 gram would be 8 grams of oxygen required. Now, in terms of mass, more mass of oxygen is required compared to hydrogen, because hydrogen is a lighter gas. But the particles, which one has more particles? Obviously, this one has more particles reacting, right? So the total mass of these particles combining together would give you how much gram of water? Would be actually 9 grams of water. And that's exactly what we started with, right? If you remember, we worked back our calculation as well, right? Are you getting this? So even why, now coming back to the point that why we need moles, because instead of counting these large numbers and doing the calculation how many of them will react in the correct ratio together, and identify it is equal to the molar ratio, why don't we just work with grams and moles and be done, right? Makes our life easier to get the actual mass there, which is the reality, right? So hence the Avogadro number is not just a fake number, it is a number that actually simplified everything for us, right? So hence we talk about moles. Okay. Now here's a fun question for you, right? A bit advanced, right? So a cup has liquid bromine, right? Gas, liquefied bromine gas, liquid bromine gas, right? Since it's a liquid, so you can't apply the gas thing over there, right? Uh, with volume of let's say 100 centimeter. This is way too advanced now. Okay, let's talk about, too unfair for you. Let's talk about liquid water only, right? Has a volume of 1 centimeter cube, right? uh, Calculate the number of uh, bonded electrons. Since you have done bonding, right, covalent bond, right? So I'll draw the model, so you don't need to worry about this. I'll draw the dot and cross model for you for the ease of working. Bonded electrons over there, right? Just by the volume, I need to calculate how many electrons are involved. So moles are going to make it very easy, right? So uh, since this is a volume, you do know how can I convert volume into mass? Any formula that relates the volume of mass to volume and mass together? Any formula? Hmm. Very good. Density into volume. So we need density. And remember, density of water is 1 gram per mole, 1 gram per centimeter cube, right? This is universal constant that we take as a constant, right? 1 gram per, unless the question gives you the value, we're supposed to be using these value. Again, not your level question. This is IB level question, right? So they give you volumes rather than masses to confuse you even further, right? So again, since it is only pure substance, so we can easily work this into moles, right? So I just did this gimmick to give you an extra step of calculating the mass rather than giving you the mass directly, right? So let's calculate the mass. It is 1 into 100 centimeters. So this is 100 grams of water, right? So remember, for water, usually we say that 1 kilogram is equal to 1,000 liters in volume, right? Or 1 gram is equal to 1 ml or centimeter cube, right? This is a shortcut that we use for water, only for water, because water is considered as a standard. Why water is a standard? Because of this property, right? It's unified density, right? We started measuring things by comparing its density to water, and we took water's density to be 1 as a general standard, and then we just started working on things. So again, we've got how many grams of water? 100 grams of water, right, in the cup. Right now we've got the grams, and now we can easily work, because moles is equal to given mass over molar mass, right? There are 100 grams of water. We know each one is 18 gram per mole, right? So let me just do the little calculation over here, right? We have 100 divided by 18. That is 5.56, right? Rounded off to two significant, right? 5.56 or 5.6, you can say. Two significant would be 5.6, right? Your paper demands two significant minimum, so 5.6 mole, right? So that many moles are there, and we know that this is the water molecule, right? So it has 1, 2, 3, 4, 5, and 6, right? And this is then the hydrogen, which is connected to them with the dotted electrons, right? So this is one bond, covalent bond, and this is another covalent bond. All right, do you get this? This is a molecule of water. So how many number of molecules are there? We can easily calculate from the moles, right? We know this. We just need to multiply this with Na to get the number of molecule, and each molecule has how many bonded electrons? 4. 4. 4, because hydrogen is also contributing, right? Electrons, right? Mutual sharing. Mutual sharing. The word is mutual sharing, right? So we have 4 in each. Now all I need to do is to convert number of molecules, right? How many number of molecules are there of H2? And that would be moles into the Avogadro number, which is 5.6 into 6.02 into 10 to the power 23, right? So I'm not gonna meddle with the 23, right? I just simply take the power add up, right? I do that manually. So 02, I get 33.7 into 23, right? Or I can simply simplify this now, 3.37 into 10 to the power 24, right? Or further simplified for your answer requirement to be 3.4 as rounded off, right? 3.4 is this. This many molecules are there, right? Molecules of water, molecules, H2 molecules, and how much? 100 gram of it, right? 100 gram has this many water molecules. Okay, and since I know this many number of molecules, each one has how much? 4 electrons, right? All I need to do is to just multiply 4 multiplied by the number of molecules, which is 3.4 into 10 to the power 24, right? So 3.4 multiplied by 4 makes it 13. So 1.36 into 10 to the power 25, or 1.4, again rounded off, right, into 25 electrons are there. And these are just the bonded ones. Now imagine how discrete I went into the atom and being very accurate of how many atoms are there just by knowing how much volume of water I had, right? This is the fun of playing with moles. Once you understand the concept, makes your life very easy. Are you clear about this so far? Why we use moles? This is just the example to help you understand why mole is studied, right? A lot of cases moles is difficult mole because you don't understand why you need it, right? So it is just like how you have rulers, right? It has got centimeters, it's got meters, it's got kilometers, right? So bigger unit, smaller unit, consider mole being a bigger unit of mass, right? Or volume or concentration. That's the fun of it, the beauty of it, that the moles can be correlated to all three versions, right? Which I said, to the mass, to the volume, right? It can be to the mass, to the volume, and even to the concentration and volume together. So you can, mix these things up together. As I said, you can replace these, equate these equations as well. But that's a bit advanced for now, just to ensure that if you've grasped the idea of moles, then we can build upon chemical reaction. Currently, I'm not talking about chemical reactions, right? We need to be able to apply this to chemical reactions, right? So just to begin with a simpler example of how the moles work, right? Why do we need moles? Let's say I produce ammonia, right? We do know that's a very important component for making fertilizer, although it's a reversible reaction. But for now, I'm just gonna say that this is a forward reaction, right? I'm just gonna make it a forward reaction, hence I'm using the star pen, right, to indicate that this is just an assumption, right? So let's say this is what is happening. Uh, I say that I want to make 20 tons of ammonia because I need to supply for the global community, right? The whole world. I need 20 tons. Okay, let's make it simpler. Tons to, you do understand that 1 kg is equal to 1,000 grams, right? And 1 ton is equal to 1,000 kilograms, right? So it's just a matter of 6 zeros between tons and grams, right? That's it. So I'm just going to start with 20 gram for now. That I want to make 20 grams of ammonia, right? How much of this do I need? And how much of this do I need, right? I don't know. I don't need, right? I only know their molar ratio. That I do understand if I count the atoms. Is this a balanced equation? First of all, no. So first we need to balance this out, right? Only then we can compare the molar ratios, right? So how can we balance this? Perfect, right? So these are gases. So I need how many atoms of hydrogen, nitrogen? Two atoms of nitrogens. Add with six, and gives you two and six. In other words, I can simplify this further, but I don't, right? Because that would make it just add one more step into our calculation. I want to keep the molar calculation as simple and as neat as possible, right? So all I'm going to see is the compounds now, not their atomic ratio, right? Since I only check the atomic ratio just to identify if the equation is balanced or not, right? It is a balanced equation, so I'm just gonna put in my dividers over here, right? And I'm gonna do the molar ratio, right? That I do know that 1 mole of nitrogen, keep in mind the nitrogen complete one, not an atom anymore. I'm talking about the chemicals exactly as a whole, right? Reacts with 3 of this to give me 2 of this, right? These are how many moles. Now this is what we call as balanced moles, right? Bm, right, of the chemical equation. So write the balanced chemical equation, balanced equation, write the balanced moles underneath them, right? How many of them are there? And simply, I do know that for 2 moles, how much I need? 3 moles of hydrogen, 1 mole of nitrogen, right? To make 2 moles of this. All I do is convert this into moles and my job is done, right? Nothing difficult. So the given mass of ammonia is 20 grams. I know that the MR would be 14 plus 3 into 1, which is the hydrogen, right? N, right? N and H3, right? 3 of this. So gives me 17 grams per mole. That each mole has 17 grams. How many grams do I have? 20. So I can calculate the number of moles, right? How many moles are there? So it is going to be small m over capital MR, 17, right? Sorry, that's the MR. My bad, right? 20 divided by 17, right? 20 divided by 17 gives me 1.18, right? Moles. Now I'm going to stick to three significant figure for my ease, right? So this many moles are there. Now just from the ratio, each 2 mole gives you 3 and 1, right? So first I'm going to draw a ratio like this, right? Between H2 versus ammonia. How much of the H2 will be needed to make this ammonia, right? We do know that we have a ratio of 2 ratio 3, right? That's 1. And for the nitrogen, I'm gonna also draw another ratio for this, right? And I know for to making 2 of this, I only need 1 of this, right? This is coming from here, right? This is 2 to 1 and like 3 to 2, right? These two ratios I'm taking out independently, right? This is the green one and this is the yellow track I took for the hydrogen. Did I? Yeah, okay. So now let's run the calculation. I don't know this. This was y and this was x, right? X ratio, how much I have? 1.18. And y ratio, how much I have? 1.18. Simply cross multiply and get the answer, right? So over here, y would be, yeah, yeah. Yeah, sure, sure, sure. Give it a try. So, to understand this, now we just do a cross multiplication of this and solve our case, right? Over here, the y would now become, let's see if I just simplify. I mean, this is, right, 3 over y ratio 2 over 1.18, right? The simple way we do mathematical relations, right? I'm just doing that over here. Nothing usual, right? You write there balanced ratios and then the ratio that you're supposed to be working. Just equate those ratios together and you simply can do a cross multiplication. Then it would be 3 into 1.18 divided by 2. So you would know how many moles are there for the hydrogen that are needed, right? So again, 3 into 1.18 divided by 2 makes it 1.77, right, moles. And how much would I need over here for x? That would be now x is equal to 1 into 1.18 divided by 2, right? Again, it's a simpler ratio that you have, x ratio y is equal to w ratio over z, right? So you can equate this as, if you want to get the y, so y is equal to x into z divided by w, right? This is what I'm simply doing as a mathematical gimmick here, right? Just algebra, basic. So 1.18 divided by 2. So I have 0.59 moles, right? So I've got the exact moles that I need for each one of them to give me exactly 20 gram, right? So I can now convert these into grams. How I can convert this into grams, right? I need, again, N is equal to M over MR, right? I know the MR of hydrogen gas, which is 2 grams, and the MR of nitrogen, which is 14 grams, right? So MR is 2 grams, and over here the MR is actually for 28 grams, right? Sorry, 14 plus 14 is 28 grams per mole, right? I need the mass. So the mass of hydrogen used would be number of moles into the hydrogen, 2 into 1, 2 into 1.77, right? So that would be giving me 1.77, 3.54 grams of H2 needed, right? And how much of the nitrogen would be needed would be, again, the same way we just do this. Given mass would be N into MR, right? I've just flipped this equation over here, right? Flipped it. So again, the mass moles are 0.59, so 0.59 into MR of nitrogen gas, which is 14 plus 14 being 28, right? So 0.59 into 28 gives me 16.52 grams, right? So in other words, I need 3.54 grams of H2 to react with 16.52 grams of N2 to give 20 gram of NH3. Are you clear? How we can use the moles to run our calculation to identify how many moles are there. To quote another more complicated example, let's talk about this, right? We have HCl that reacts with calcium carbonate, gives you calcium chloride plus, right, Cl2 plus H2O plus CO2. Right now, here's a gas as well, so molar volume will come into effect. And since this is aqueous, so our N is equal to CV, concentration into volume, this thing, right? This is solid, this is grams, so this is N is equal to M over MR, right? And this is again aqueous solution or solid, right? And this is liquid, which is mass. We can easily convert it into mass as well. And this is a gas, so N is equal to V over Vm, right? For the rest of them, we can use this idea. For the solutions, we use this equation, and for gases, we have to use this equation, right? In other words, volume, because I cannot weigh the gas of a reaction, but I can actually measure how much volume or space it is taking, right? How much the balloon has inflated. Or the syringe, you remember the syringe, collecting a gas syringe experiment in which we collected some gas in the syringe, right? So just to give you an idea, like let's balance the equation. I think this balances the equation, right? So in other words, I need two of this, one of this, one of this, one of this, and one of this, right? I simply ask you, if I want to get 0.25 mole of this, how many moles of HCl do I need? 0.5. Perfect, right? Okay. If I have 2 mole of this, right? How many moles of hydrogen would be produced? Or water, sorry, would be produced in this reaction. If I start with 2 moles of calcium carbonate, right? 2 moles, right? Because they're equal. Perfect. Okay. Now you get the idea. You can easily convert them into grams if you want, right? And if you know the MR of this, if you know the MR of this, right? And since this one is volume and this, so that's a different thing. If you know the concentration over here and the volume, right? Both C and V are required for this. How much volume of acid is there, how much concentrated. Or if you're given the mass directly, then you can also use the MR formula, which makes it easier. But usually with acids and bases, they don't give you the masses, they give you the concentrations, right? Because those are solutions. Okay, and this would be done by MR because water is not a solution, it's a liquid, so we can easily weigh this. This would require molar volume to begin with, right? Because we need to compare this to the molar volume to get the moles. All right, so you can easily compare the ratio between any two components, right? Any two component, not necessarily that I need to know this exactly to solve all of them. If you know one of them, even one, right, you can crack the whole chemical equation no matter how big it is. That's the fun of using moles, because we do know that they will only react in a specific number of atoms working together. For example, calcium is +2 and chlorine is -1. Then we are sure that wherever they join together, they're going to form a compound CCl2. It would never form, let's say, CCl4 or CaCl single, right? Can't happen, because the charges do not dictate this. It only neutralizes when there is +2 over here and -2 in total over here, right? Which we call as electronically neutral. So that is why I'm going to give you another hint over here, that atoms only react in fixed proportions to form a chemical, a specific chemical compound, right? Obviously for different compounds will come across different formulas as well, right? They combine in more than one fixed ratio, but each one is a different compound. For example, if I talk about N2O, N2O2, or NO2, now in which we see that oxygen and nitrogen are combining in more than one ratio, but every time I talk about N2O, then it is going to be over here, like it is going to be 2:1, 2:2, and 1:2. So remember, for each distinct chemical, their ratios would be fixed. It is not possible that NO2 would have any other ratio, right? Nitrogen dioxide, we call it, right? And the nitrogen peroxide, or this superoxide, right? Both of them would have their own independent. For example, water is always found in 2:1, right? You're not going to have water as H4O6, right? Can't happen, right? Water will always be like this. No, it's not about look like. There is a compound, hydrogen peroxide, H2O2, which is different. So their chemical properties are extremely different compared to water. This is very, this is caustic and reactive compared to water. Keep in mind, this is extremely caustic, extremely reactive. It's a what we call as hydrogen peroxide, right? Or peroxide, commonly known as, right? Also available in the pharmacies for wound cleaning, right? Because it will kill any bacteria, no matter how strong it is, right? How strong the shell is, because it's very reactive. So very dilute version of this is applied on the wounds, to on an exposed wound, so that any virus that is multiplying or bacteria multiplying on the wound would immediately die. It would also damage your cells, but yes, your body can easily recover those cells. But if the infection spreads, then it will be harder to recover, right? So we just, apply a little bit of hydrogen peroxide on some wounds as well, right? Critical wounds, to keep them clean, right? So compared to this, hydrogen peroxide will always have this ratio, and water will always stick to this ratio. And due to their fixed ratios, their properties are fixed, right? Independent, in other words, I said chemical are used, right? Independent chemical, each one. So by chemical, I said that chemical properties must be different for each chemical to be distinct, right? The chemical properties are well defined, they're different from each other. That's what I call a chemical, right? Are you clear about this? Okay, let's close.